real solutions to polynomial systems using numerical algebraic geometry.
Thank you, Alex, for the invitation, and thanks, Victor, for the discussions earlier today. So I want to tell you about computing real solutions using numerical methods and without going into too much detail. So I want to show lots of pictures, and hopefully the movies work. If not, I'll show you on my small computer the movies. So let's get going. So here's the general setup. We have little n polynomials in capital N variables, x1 through xn, and we want to study the solutions to these polynomial equations. So the fundamental problem in numerical algebraic geometry is to compute numerical approximations to each isolated solution. So if you have an isolated solution, give me a numerical approximation to it, for example, so that Newton's method will quadratically converge to that solution. If there are positive dimensional components, describe them in some numerical approach. The approach in numerical algebraic geometry is based on witness sets. I don't want to talk about any of that today, but there is a canonical way to describe the irreducible components in numerical algebraic geometry. So what we're really interested in is real things, and why should we be interested in real things is because they show up in applications. So I'm going to spend a minute or so talking about different examples from applications that I am personally involved with or have been in the past. So the first one is if you have a chemical, this one comes from explosions. So you have some hydrogen and you light it. The hydrogen goes boom. What happens is you're going to get different time scales of how that reaction is going to happen. In the long time scale, there's going to be an equilibrium, and then in shorter time scales, there's going to be various transitions that happen. So what we wanted to do was study the equilibrium, which is this point here where everything collapses to it, as well as these other time scales. And you can get what's called a slow invariant manifold that will converge to your equilibrium. So it's a nice real object, real one-dimensional object that sort of describes how your explosion or your chemical reaction is happening. So that's a nice real solution defined by polynomial equations.
What's physical interpretations of these variables here?
Yeah, so here is your equilibrium point. So all of the trajectories go into that equilibrium point. The shaded region is the physically meaningful region, and the unshaded region is not physically meaningful. So there's some kind of chemicals that are happening there. And now you want to see how does it transition to the equilibrium over a long time scale, sort of a slow moving time scale. So there's certain things, like let's say you start here, it's going to converge quickly to this and then slowly converge to the equilibrium. So there's this invariant manifold that describes the how things deform to the equilibrium. And it's defined by real polynomials.
Well, just two variables here.
Yeah, this one's only two variables. I couldn't draw the picture for the actual one that we're interested in, which I think has 18 variables. So you have hydrogen, oxygen, nitrogen, all different things that happen in the air. Yeah, so that one's a toy problem, but you can imagine a lot more species. If you set up systems of differential equations, you can discretize them, and that will give you polynomial equations. So this is an example of a tumor model, and we wanted to see what happens as certain parameters are changed. And this is a static picture, but as certain parameters are changed, instead of being a sphere, it sort of deforms and back. And so you can study what happens as certain parameters change. Are there bifurcations that occur? Where do the bifurcations occur at? Those are all given by solutions to polynomial equations. This is capturing shock. So you have some energy, and then it has a shock that happens there. You want to know where does the shock happen, and how can I get resolution around the shock? Shocks you should think of corresponding to singular solutions. So there's some singularity, and you want to study sort of that singularity. In this case, it's a reflection off the boundary, is exactly what the shock is, what's happening here. So these turn into very large systems of polynomial equations coming from hyperbolic differential equations. So you take a hyperbolic differential equation, you discretize it, you get polynomial equations, and our method for finding these was roughly in experiments with linear complexity, while the best known are quadratic complexity. So for these kinds of hyperbolic equations, using numerical methods, numerical homotopy methods are much better. Here's a problem that we solved in real enumerative geometry. So let me explain this. Take 8 lines in space. Okay, so you have 8 lines in space that are given, and now you want to count the number of conics that intersect those 8 lines. So in this picture here, I'm rotating space, but these are the same 8 lines, and you see these conics intersect those 8 lines. So this is one conic plotted here. An enumerative geometry problem says count the number of conics that meet 8 given lines, and that answer is 92. So there are 92 conics that meet 8 given lines, assuming they're in general position. And now the question in real enumerative geometry is, can all 92 of those be real? Can you find 8 real lines so that all 92 solutions are real? And working with an undergrad at Texas A&M, this is the first known example of 8 real lines where all 92 solutions are real. So the magenta color, I believe, is one of the 92, and all the other 91s look very similar to that. So this was a nice undergrad paper solving this problem in real enumerative geometry. You can also try and design mechanisms. So for mechanisms, you're interested in real things. You have to actually physically build them. So your leg lengths have to be positive. Things have to actually behave nicely. This is a picture of Alt's problem. An Alt's problem says, pick 9 points in the plane, find what's called a 4-bar mechanism that interpolates those 9 points. From an engineering standpoint, this one is absolutely useless because self-intersections these self-intersections are singular, but it makes for a nice picture on the screen. So that's why I put it up there. You can also have mechanisms that have a motion to it built in. So here you're actually turning a crank to move it. Here, this one is a fixed object and it just moves on itself. You can actually wiggle it. And it defines a degree 40 motion curve. This one was taken from the IMA project in 2006. So this was designed by Charles Wampler and Doug Arnold for that project. So the point of me showing you this slide is real solutions show up a lot in applications. We want to try and understand them and compute them. Okay, let's see if the movie's going to work. Yes. Don't really need music to it, but I guess the music will be playing. Here's an example of a mechanism that 2 engineers at UC Irvine wanted to design to match the flapping of a wing. So wing flapping is a very hard process to synthesize. And so what they did was they picked points on these curves and then tried to find a mechanism whose coupler curve passed through those. We wrote a lead story a couple months ago in SciEm News that you can sort of hear a popularized version of how this happened. The system that was solved was 70 quadratic equations. So 70 equations of degree 2. And one of those solutions is exactly this mechanism here that you, let's see if we can start over in some way. So this mechanism here was one of the real solutions and it has nice physical characteristics. So they're going through all the nice physical characteristics. Low torque, high ratio gear, so you can spin this really fast to get the nice fluid motion as your wings are flapping. Okay?
So how many variables and how 79?
This one had 7. So there was a reduction that the engineers did. This one was 70 equations in 70 variables, all of degree 2.
So here you mentioned Bertini. Is it the software? Or
Yes. Yeah. So Bertini is a software package. Go to bertini.nd.edu and you can download it for free. Yeah. So Bertini is software to be able to numerically solve polynomial equations. Okay, so what do I want to do today? What I want to do today is talk about other local methods to be able to find real solutions. So you're probably intimately familiar with Newton's method. Newton's method is a local method to be able to iterate. There are other approaches to help you understand the local solutions. And now, once we can find local solutions, can we turn that into a global solution? Can we say we have all of the real solutions? So if there's time, I'll tell you about that. If not, then that's okay. So this covers joint work over the span of several years. This latest paper on this local to global was just finished this week with Daniel Brake and a graduate student, Alan Liddell, at Notre Dame. Okay, so the fundamental challenge with real solutions is on the dimension. If I take one non-zero polynomial over the complex numbers, that defines a hypersurface. It always defines something of dimension n minus 1. One equation, n variables, always a hypersurface. But now, instead of going over the complex numbers, you go to the real numbers, and that's completely false. You can have the empty set, which I'll go with the convention that has dimension minus 1, all the way up to the full hypersurface of dimension n minus 1. In particular, any real algebraic set is equal to the real points on a complex hypersurface. So things can be as bad as you want them to be, and this hypersurface will define any real set. So just to explain or give you an example, if I sum up the squares of all the variables and add 1, there's no real solutions where that can be equal to 0. Because when you square a real number, it becomes positive. These are non-negative. These are all non-negative. If I add 1 to it, now it's positive. There's no way to be 0. So this one is empty set, and I'll call that dimension minus 1. If you sum up a portion of them, or sum up squares of a portion of them, that means that these variables all have to be 0, and then the other ones are free, and so you have j free variables, so you have dimension j. So here's trivial examples showing this behavior. So dimension is always the hard part with real solutions. So let's look at an example. If you take y squared plus x squared times x minus 1 times x minus 2, this is the real picture of it. Over the complex numbers, it's an irreducible curve. So it's a nice, beautiful, irreducible curve. And this is the real picture. All these points over the real numbers and over the complex numbers are dimension 1. If you have a real point, you can move it in a one-dimensional freedom. Whereas this point is isolated, so its dimension is 0 over the real numbers, but it lies on this curve. So the complex is it has dimension. So this is going to be the fundamental challenge with real solutions. Is this difference between the real dimension and the complex dimension? The nice thing is that whenever there's a difference, it has to be singular. So if it's smooth, then it has the right dimension and there's no issue. If there is a difference, then it's singular, and then you have to study it much more. Okay. If if things are isolated over the complex numbers, so this is what I just got done explaining to several of you in Victor Pan's seminar. If things are isolated over the complex numbers, then of course they're isolated over the real numbers. So in this equation, this system defines a line, x equal to y, and then there are two solutions coming from the intersection of this degree 2 and degree 1 equation. This is the picture over the complex numbers and over the real numbers. A complex line, a real line, and two isolated points. So here, everything can be found just by using complex solution solving. So several years ago, I went on an adventure to try and find an application where things were isolated over the reals but not isolated over the complexes. Because that would really cement that we need new tools to be able to do this. Here, if they're both isolated over the complexes, there's no issue. But what about isolated over the real numbers, but not over the complex numbers? For example, this point here is isolated over the reals, but not over the complexes. Can you come up with an application where this happens rather than some contrived example? And I found one. And so this was an engineering paper by a collaborator of mine, Charles Wampler, and two of his co-authors from 2007. So let me explain the picture. Each one of these joints are rotational joints, so they can rotate. And each of these legs have a fixed length. Of course, if I take this object, I can move it in space. That's not interesting. So what you have to do is you have to fix a frame of reference. So pick a triangle, for example, this triangle, and that will be your fixed frame of reference. And now take the other ones and see if they will deform. See if they can actually move, rotate them. Okay? So this is 17 equations, they're all degree 2, in 18 variables. This is underdetermined, and so immediately over the complexes, it has to move. It has to move. There's one fewer equation than variables. However, this particular case, this configuration here does not move. It's rigid. You can use it, you can stack things on it, it does not move. So here's an example that's isolated over the real numbers, but not over the complex numbers. So now we want to try and understand what's happening in this example. So the first thing we got to be able to do is be able to compute that. How do you locate something which is not isolated over the complex numbers? And there's an approach by Seidenberg from the 1950s to do this. So here's the real solution set. And he said, pick a point that's not on the real solution set and look at the distance function. And then find where you reach a critical point in the distance function. So a critical point of the distance function means that the vector between your point and here is perpendicular to the tangent space. So that's the critical point. You're going to find a point on every connected component that minimizes this distance. If it's compact, you'll also get the maximizer of the distance. But you'll also get all of the other isolated points. So you can find all of these isolated points by looking at this critical points of this distance function. Okay, so here's the definition. So z is a critical point if there exists a lambda such that this equation holds. This equation just says that the vector between the point that you pick and the point on the curve is perpendicular to the tangent space. Okay, so it lies on my curve and it's perpendicular. Everything that's a local minimizer is a critical point. Everything that minimizes the distance is a critical point, but also every singular solution. If this is rank deficient, then you can just take this to be 0 and you trivially have a critical point. So, how do we get around the case of instead of finding every singular solution, we only want to find the ones of interest, and that's where homotopy methods are going to come in. So let me give you an example to sort of cement this idea to you. Suppose I look at the equation x minus y quantity squared. Any point that satisfies that equation, the gradient is equal to 0. So every point on that line is a critical point. So going from the original thing to the critical points hasn't gotten me anything. I still have everything. I haven't sort of isolated the minimizer. So what do? Well, you perturb it. You throw in a perturbation. So for example, if I throw in t equal to 1, I get these 2 points here. I get these 2 points. And now as t goes to 0, these 2 points converge to my solution, which minimizes the distance from this fixed point to my line. So by doing this perturbation, solving that, and then looking at the limit as t goes to 0, I get these critical points that I want. And you can prove a theorem that this works. So in general, you have to take a random vector and then perturb, and then deform in that direction. But what you get in the end is a finite set of points. Finite, that's the key. Finite set of points that contains a point on every connected component. So this is a connected component, there's a point on it. This is a connected component, there's at least one point on it. This point is itself a connected component, I get it. This point, exactly, I get that. So this is a set that contains a point on every connected component. In particular, it contains all the isolated solutions. And if this set is empty, that happens if and only if there are no real points. So deciding whether there are real points or not is equivalent to deciding whether this finite set is empty or not empty. So you're turning something that's potentially hard into a finite test that may still be hard, but could be much easier. So now we applied this to our mechanism, and we get these 2 types of critical points. These are the ones that we've already saw. So this is rigid over the real numbers, but over the complex numbers it moves. And now you can imagine sort of cutting this off, flipping it around, gluing it back together in the right way, and you get these kinds of mechanisms. And now fix a triangle, and now you can see that this guy will swing back and forth. So you fix a triangle, the other guys will swing back and forth. So you actually get real motion here. So this has real motion, this is rigid. So those are the critical points you get. So now the question is, okay, I get all these points. How do I know whether it's isolated or not over the real numbers? Okay, so what's its dimension? What we want to do, and I don't know if we found this yet or not, I think it's still open, is we want to find a method given a numerical approximation that computes the dimension of the real set through it. So everything here is numerically approximated, and we want to use locally computable information in a numerically stable manner. One approach to do this globally is something called the cylindrical algebraic decomposition. So that gives you a description of all the solutions, and now you just find, where does this point lie at in all of the solutions. Typically, this is very hard to compute, though. I only want to focus in on a certain aspect, and so this may be overkill. Another approach is to use tangent cones. So Morris tangent cone algorithm, which is sort of a generalization of Grosvenor basis in some way. Could do this, but then you have to worry about numerical stability issues. You could try a subdivision approach and sort of just look in this region and try and subdivide it. That would also work. The two approaches I want to tell you about or mention give us upper bounds and lower bounds using only information at that point. So in 2009, we developed a method using Macaulay dual spaces that will tell us what is the dimension of the complex numbers through that point. And so, of course, this is an upper bound on the real set. Another approach is to look at the singularity structure, and I'll show you pictures of this next, is look and see which points have the same singularity structure as my given point. And the dimension of that will be a lower bound on the real solutions then. So here's an example. I brought this with me. So I have this here in 3D. So this is what's called the Whitney umbrella. If you pick a point up here, you can move that point freely along here. So it's a nice smooth point. You can move it freely in 2 dimensions, up, down, left, right. So up here on this umbrella, there's no singularity structure. Everything is smooth, so it's nice in 2 dimensions, sharp. Okay, now you look at what's called this handle. So this has a self-intersection, so you see that these intersect itself here along this line. If I'm up here, you want to know, okay, what's the dimension of all the points that have the same singularity structure? Well, that's one-dimensional because all these points are a self-intersection. So up here, the singularities are 1 dimension, but of course it's 2-dimensional because I have these sort of planes that pass through. So it's a lower bound that's not sharp. Down here on the handle, you can't see it, but it also has it's also a self-intersection, and the self-intersection is over the complex numbers. That's why you can't see it. And so it also has the same singularity structure on this 1-dimensional object, and it's sharp. That's the right dimension. And then the interesting point is this pinch point here, where the handle actually attaches. That pinch point is different singularity-wise than every other point nearby. So it's isolated. It's isolated in terms of its singularity structure, but there's still 2 dimensions of real spaces passing through there. So the complex dimension is an upper bound. This isosingular dimension, this singularity dimension, is a lower bound. If they're equal, so 2, everything is equal, you're done. If they're not, you have to do some more work. Okay. The simple fact is irreducibility is just not strong enough. So irreducibility is something over the complex numbers. So this curve is irreducible over the complex numbers, but you see over the reals, it has different behavior. The Whitney umbrella is irreducible over the complex numbers, but it has all this different structure. So irreducibility just is not strong enough. So you change your definition. From global irreducibility, you go to local irreducibility. And so let's demonstrate it by this curve. So here's a nice degree 5 curve. The Empire State Building's a couple blocks away. You go to the top of the Empire State Building and you look down on this curve, and this is what you see. A nice degree 5 curve. Irreducible, you can't factor it. But that doesn't tell you anything about what's happening, say, at the origin. So what you need to do, instead of going from the 50,000 foot view, is you need to go to the microscopic view. And that's exactly what this local irreducible decomposition does. So you pull out your microscope, and now you zoom in, and what you see at the origin is you see this nice intersection. So globally, it's irreducible, but locally, it looks like the intersection of 2 lines.
What is the definition of local irreducible?
I'll give it to you in 1 second. So at least from a pictorial view, you can see that these should be different components. Okay, so to answer Chi's question, here you go. The definition of irreducible means that the smooth points are connected. So you take out all the singularities, and the smooth points are connected. The connected components of the smooth sets, those are irreducible. Locally irreducible means in a neighborhood, my smooth points are connected. So first thing is, what does it mean to be in a neighborhood? But let's assume that you can pick a neighborhood, and now you remove the singular points, and you look and see what's connected, what's still connected. Those are the locally irreducible components. This is not something we invented. You can look at germs of functions and define the same thing. So these are well-defined things using complex analysis. So complex analysis tells you exactly what this neighborhood is and how things behave in that neighborhood. And you can do everything that you want globally, you can do it locally. So locally, your solution set can be broken up into these locally irreducible components. Each of these components have a well-defined dimension. They have a well-defined degree, just like from the global perspective.
So in your previous case, the point, the curve is globally irreducible at the origin, but locally reducible.
Yes. So this is a globally irreducible curve, but it's locally reducible. You take out this singularity point and then think over the complex numbers. This is a line that's connected except for that point. This is a line that's connected. I have two connected components.
Then how come it's irreducible globally?
Because this doesn't factor. The easiest way to see that is this polynomial doesn't factor. Another way to see that is you remove the singular points of this, and it's still connected over the complex numbers. Those are equivalent. Factoring this polynomial is equivalent to saying that the smooth points are connected. So globally, the smooth points are connected, but now if you locally look and you remove this singular point, the smooth points aren't connected. So somewhere outside here, there's a loop that connects these guys. You just don't see it in the microscopic view.
But I also don't see it in the bigger picture. Where might the loop be?
Yeah. So the bigger picture, I zoomed out too far, but the bigger picture should look like this.
You're talking real or
Complex. Complex. So I can only draw the
space, right?
yes, I can only draw the real points on it.
Oh, right.
But,
Yeah.
but you have to make believe over the complexes. This guy, every point here is connected, and then when you cut it here, you lose the connection between here, and so then these guys are reducible. Two components. Very good. Okay, so this is all famous complex analysis. The famous paper, Gaga paper, that relates analytic geometry to algebraic geometry holds here. There's nothing about these guys being polynomials. All you really need are analytic functions to make this work. Okay, so let's go through some examples. So if I have a smooth point, then what it looks like is it just looks like the tangent space. So if you have a smooth point, it just looks like the tangent space. The dimension is the dimension of the tangent space. The degree is 1. It really just looks like a tangent space. So smooth points really just nice, irreducible things of degree 1. It really behaves just like your tangent line or your tangent space there. So the only interesting cases are the singular points. So here are two examples where I've zoomed in on the origin. Both of these are globally irreducible of degree 3. Globally irreducible of degree 3, but now you just zoom in on the origin. When you zoom in on the origin, this looks like the intersection of two lines. So this is reducible. So this guy decomposes into two components where this cusp is irreducible. You can't break that cusp into pieces. What's interesting is globally these have degree 3, so they're defined by degree 3 polynomials, but locally the degree is 2. The way to see this is count the number of intersection points with a line nearby, and a line can intersect in 2 points here. And again, a line intersects in 2 points here. The third point is somewhere else that it intersects. You know it has to intersect in 3 points because it's degree 3. It's just somewhere else far, far away. For example, in my picture here, if I take a line like this, it intersects in 2 points and then this third point. And now as I deform this line so that it passes through my singularity, this one converges to my singularity, where this guy converges to somewhere far, far away. So you count the number of convergent paths to your singularity, and that's exactly this degree. So this is well defined using complex analysis, this degree. It really is the number of convergent paths as you deform your linear space. Here's another example. Degree 5. The origin, globally irreducible, the origin is this point here. So globally irreducible, but now when you zoom in on the origin, it breaks up into 3 components. You have this line, and then a cusp coming in there. So you can have lots of nice irreducible components happening. This is one where it may not work. So I'll pull out my laptop and show you guys here in the room. So this is what's called a folded Griffiths-Duffy platform. There you go. So what this does is this will screw out, it'll unfold, and then twist around and fold down, and then come out the bottom side and twist around. So it has a fold, and then it spins out. I can't spin my arm all the way around, but then it comes back down. And then the unphysical part is it passes, 2 solid objects pass through each other, but make believe that you can do that. Then it spins down and it spins back around. Okay. So this is a nice chorded curve that passes through this so-called folded pose. So it's folded, and then you unfold it, spin it around, and it folds back down. Okay. Good. That worked. So this is a curve in 6 dimensions, but you can make believe that it looks like a figure 8. Fold it out, spin it around, and back down. So it looks like a figure 8. Fold it out, spin it around, and come back. So that's a chordate curve. And then if you zoom in at the origin, it looks exactly like this intersection. So there's 2 components there, each of degree 1, meaning do I spin this way or do I spin that way? And so locally, you understand the geometry by just looking at the mechanism. Does it spin this way? Does it spin that way? So 2 components there, but globally they're connected.
Could
Go
you
ahead.
explain more how do we get this curve? Do we follow a particular point on the?
So how do you actually do this? Okay, so let's use my picture here. So what you do is you take your curve and you intersect it with a linear space of complementary dimension. That gives you the degree number of points. And now what you do is you do a monodromy action around this point. So you go over the complex numbers and you go around this. And you see what happens in the monodromy. So what you're doing is you're finding the local monodromy group at this singularity. And if you can find a path to go from this to this, then they have to lie on the same component. If you can't find a path, then they have to lie on different components. So what you're doing is you're really computing the local monodromy group at this singularity. And that will tell you how to break this up. So, good question. Local monodromy group, I showed this earlier. So this corresponds to x squared minus t is equal to 0. So there's a singularity at t equal to 0, x equal to 0, multiplicity 2. And so now you want to see, how does this behave locally? So, of course, the picture, it looks like this. Is this one component, or is this two components? Well, what you do is you slice it. You take care of it, good. What you do is you slice it, and now you take t equals e to the I theta. So you take a loop in the complex plane and see where that goes when you come back. So here's my picture. This is the real part that lines up exactly with this. And then I actually have a third dimension here that I don't on the board. And so I want to do a loop. So I take my point here and I do a loop. And I come back and I end up here. Since I have a connection from this point to this point, they have to lie on the same irreducible component. And so here the monodromy group is S2, and this is locally irreducible as well as globally irreducible. So you can get from this point to this point by doing a monodromy action.
How does that figure 8 shape curve relate to the local monodromy group?
Yeah, so there you go. So slice here, and you get 4 points. And now when you do a local monodromy group, this point goes around and comes back to itself. This point will go around and come back to itself. This one will go around and come back to itself. And so what you'll see is these 2 points stay on that same component, and they don't move.
How do we know that they don't move?
It's equivalent to this. So instead of x squared minus t, it's equivalent to x squared minus t squared is equal to 0. Okay? So this factors as x minus t, x plus t. Once you're on an irreducible component, you don't need that irreducible component unless you pass through a singularity. That's the definition. The smooth points are connected. They're the connected components. So once I'm on a smooth point, I go around and I come back to that same one. And it's because it factors. It really is 2 components here. So locally, this is the picture. Globally, there's some higher order terms that disappear when you zoom in on the local picture. Yeah. Good question. Okay. So what happens with this curve that I showed you? Well, these guys are all smooth points. So there's absolutely nothing that needs to be done. It's a smooth point. It's real dimension equals complex dimension, done. Let's look at this point. It's a singularity. And you look and see what happens to the components. It's 2 components which are complex conjugates of each other. So it's really 2 lines that are complex conjugate components. Think about x squared plus y squared. What is it? This is x plus iy, x minus iy. So if I have a point here and I complex conjugate it, I land on a point there. This is exactly this problem if you look at the lowest order terms. So the lowest order terms is x squared plus, or 2x squared plus y squared equal to 0. And that's exactly what's happening here. So this point here factors into 2 components which are complex conjugates of each other. If it's not invariant under conjugation, they have to intersect in smaller dimension. So instead of this being 1 dimension, it's actually 0 because of this complex conjugate action. So just by understanding the local components, you can see that this is zero-dimensional. This is exactly what happens for this object. Two complex components intersect there. They're complex conjugates of each other. Therefore, the real points have to be contained in the intersection, and the intersection is zero-dimensional. So this shows that this point is rigid. Okay, let's go back to the Whitney umbrella and think about the irreducible components along the singularity. Remember, the smooth points aren't interesting. They're just the plane. So the only interesting ones are the singularities. Over the reals, you can have the top of the line, this point, and the bottom of the line. Those are the three interesting pieces. Okay, so on the top of the line, you can physically see it. The top of the line looks like this plane here intersected with that plane. So the top corresponds to two components of degree 1, and they're self-conjugate over the complex numbers. If you go to the pinch point looks like a cusp, and it's irreducible of degree 2. Okay, those aren't too interesting. Now you go down to the bottom of the handle. The bottom of the handle, you get complex conjugates. Again, it's intersection of planes there. It's a self-intersection, but those guys are complex conjugates of each other, and therefore the real dimension has to be smaller. So, you can prove the following theorem. If the real points are codimension 1 inside the complex points. So here my complex points are 2 dimensions, but here, let's look here, it's only 1 dimension. Theorem, it has to be complex conjugate components of each other. So codimension 1 we completely understand.
That's because you're assuming real polynomials.
Yes, of course. Start with a real polynomial system. That's the only way that works. If you have smaller than codimension 1, so for example, codimension 2. So this is one polynomial in 3 variables. So that defines something of 2 dimensions, but there's only 1 point, and a point has 0 dimensions. So it's codimension 2. Then you don't know what happens, and in this case, it's irreducible. However, if I would slice it and cut it down, so pick a random plane through the origin. Now this defines something of 1 dimension, and my point is isolated. So now my point is codimension 1 inside of that. It has to factor. It has to factor as complex conjugates of each other. So by using this, you can keep slicing down until you reach this codimension 1 barrier and see what the real dimension is. I don't have time to go through the sort of this local to global thing, but the key point that I want to point out is that the real solutions can be a much smaller set than the complex solutions. So a trivial example is take a univariate polynomial of this form, x to the 50th minus 1 equals 0. 2 real solutions, 1 and minus 1, but you have 50 complex solutions. You can make this as arbitrarily bad as you want, and you can find the real solutions very efficient. So let me tell you, let me at least cite some papers. In applications, so this comes from, you have a potential energy function, and you want to know what are the critical points of your potential energy. In particular, you want to minimize your potential energy. So find the critical points. So V defines my potential energy, and I want to find the minimum, and to do that, I find all these critical points. So that's a system of polynomial equations. There exists some nice work in theoretical chemistry, starting in 2002, on different approaches to be able to find these exactly in this case. So when you have a potential energy function and you look to find the critical points of that. We extended it recently in another paper. So you can quickly search this potential energy function and find lots of real points. The problem is you don't have a global stopping criterion. How do I know I found all of them? And so this is work that we just finished this week and put on the archive if you're interested, is a way to say, I have all of them stopped. So there's this parameter J, and J corresponds to the coupling strength of these. So you have different particles, you want to know how much do they interact. If you have weak interaction, that's when J is small, and if you have a lot of interaction, J is big. So when the coupling strength is small, your local sampler very quickly in, say, a second or 2 seconds, quickly zooms around and finds 3 to the 9th solutions. 3 to the 9th is interesting because that's the Bezout count. Therefore, all complex solutions are real, and you're done. There's nothing to beat. You have everything. When you increase the coupling strength, the number of real solutions drops. So in particular, from 3 to the 9th, it drops all the way down to 3. So now you have 3 real solutions, 3 to the 9th complex solutions. Again, your sampler quickly finds these 3 real solutions. How do I know I'm done? And we developed an approach based on semi-definite programming that validates we found all of our solutions. Stop there. Okay, so if you're interested in more aspects of numerical algebraic geometry, please consider attending our workshop. So website's at my homepage there. In May at the University of Notre Dame. It's in northern Indiana, 90 miles east of Chicago. There's a nice direct flight from Newark to South Bend, so you don't even have to go through Chicago to get there. If you're a grad student or postdoc or other early career faculty members, we have travel funding if you're interested. So please come and join us. Thank you.
Thank you. Any questions? More questions?
Yes,
Go ahead.
It's not like a question. So the only before your talk, the only method that I know to find the minimums are the gradient descent.
Yes.
Algorithm.
Yes.
So how your algorithm?
Yes. So one of the ways to find real solutions are Newton's method or secant method or related approaches. Local optimization like gradient descent. You start with a point and you try to get it down to 0. And then these other critical point methods. So from the heuristic point of view of trying to find local solutions quickly, they're very nice. The problem is you never have a guarantee that they've all been found. So you can try gradient descent method millions of times very quickly, but how do you know when to stop? And so now we have a stopping criterion that says, I have all of them, you don't need to search.
So what is the solution again?
Sorry?
How do you know that you have all the solutions again?
Okay, so it's based on semi-definite programming of the real radical. So the real radical is the ideal generated by the real solutions. And there's this nice criterion here that is the set of all polynomials such that you raise it to an even power plus the sum of squares is in the ideal. Okay. So what you do is you generate a sample set and you find polynomials that vanish on that sample set. So since S is contained in this real variety, your real variety here to show is the reverse containment. Show that each one of these HIs is contained in there.
So are these HIs computed?
See, that's where the challenge comes in. So one approach is to use interpolation, is to interpolate your sample set to generate polynomials. If there are structure in your things, then you can compute these much faster. And you don't have to do the full combinatorial explosion of interpolation.
So you mean you have sample points already?
Yes. So you use these
on the variety.
on the real variety.
But these are algebraic numbers. I mean, algebraic coordinates and all those.
Yes.
Things. So you're literally going to compute with those guys, or?
So there's a difference between numerical computation and symbolic computation.
Right.
So when you say you have these, I assume I have a numerical approximation of these algebraic numbers. And now I numerically approximate them. These polynomials here have to have coefficients, which again are algebraic numbers as well.
Right.
This, my original variety, I started with a coefficient field here, so I can use that to sort of try and symbolically approximate or symbolically recover these polynomials. So, but with all of that said, we're going to use a numerical sums of square program in the end. And so I don't know how to validate sums of squares programming from a symbolic point of view. All I know is how to numerically validate. So how do I know that something is or is not a sum of squares? And be able to rigorously prove that. So there's a lot of numerics happening here that I don't know whether I can do symbolic verification on or not.
So you have some examples where you succeeded?
Yes. So here's an example with positive dimensional components. In this one was very easy to come up with the actual symbolic answers. So this one we could symbolically see it had to be the square root of 1. And so once you know that, then these polynomials are easy to generate exactly. So the difficulty comes when these polynomials here have algebraic numbers in them. What's the degree of those algebraic numbers? And now how do I find that? How do I compute on that? That's where the difficulty comes in. But if you're looking for a numerical validation, which is typically what happens in these kinds of problems, this is a way to numerically validate it. Yep, good questions. Any others?
I think you're good.
Thank you guys for coming.